Hello everyone again. Welcome to the Trustworthy Machine Learning lecture. So this is a re-recording of the lecture this morning. The recording did not go through. There was some bug with the Zoom recording. So make sure to make sure that this does not happen from next time. Okay, so I'm going to use a different software from this time. A few announcements. The group assignment is done. So you're going to find an email saying which members you have, right, in your group and the name of the group, which is named after some star name. If you spot any error, then please let us know immediately. If we wish to drop out of the course, then please also let us know immediately. Then we're going to reorganize the groups. When you're submitting exercises, please indicate the group name on the collab sheet. Otherwise, we cannot identify who submitted the work, which basically happened with exercise 0 quite a bit. There will be, or there was actually tutorial after exercise 0. For that, the recording should be available, but the recording also did not go through with some bug in Zoom, or my mistake maybe. So a tutor from our side is recording the exercise 0 explanations again. So that will be made available soon. The grading is in progress, and we apologize for the delay. OOD generalization. So let's resume the discussion from last time on Q selection problem. Q selection problem is very important because in many cases you have an underspecified data set. So we are talking about cross-bias generalization, where we're amplifying the bias and the confusion due to some of the factors that are not essential for the task at hand. And when underspecification happens, it's important to kind of get the right signal to indicate what is the right Q to look at. And that is the enabler for OOD generalization eventually. So the key point here is that you actually need more information to select the right feature for the task. What kind of extra information could be there, right, to make cross-bias generalization possible? So I wish to talk about two different ingredients here. So one is to use a bit of unbiased or off-diagonal samples in development resources. So what I mean by unbiased or off-diagonal means if you look at the arrangement of the samples in the distribution, I tend to arrange the bias samples along the diagonal, right, where the color Q and the shape Q are moving together. And the unbiased samples are then all configurations, all compositions of these two Qs. And these correspond to off-diagonal. Well, actually diagonal plus off-diagonal, right? So together I refer to them as unbiased samples. The other ingredient is domain labels for each sample, okay? So additionally to the existence of those off-diagonal samples, you may also try to put some domain labels for every sample, okay? So how does the training and deployment settings look like then, right? So in the training, you're going to have the majority of biased samples with a small amount of unbiased samples, indicated by alpha %, right? So for example, alpha equals to 1%, so you're going to see a very small amount of unbiased samples, and the rest of it is perhaps just biased samples, the diagonals, right? This is more realistic setting where you can probably do something about it to solve the OOD generalization problem. One can optionally put the bias labels on top of the task labels as well. So instead of just Y labels, you have Z labels. And here Z labels are indicating the color. Okay. And with the bias label, you are actually aware of which ones are diagonal samples and which ones are off-diagonal samples, right? If the Y and Z are equal, then these are the diagonal samples. If they are not equal, then these are unbiased samples, which are highly valuable for actually debiasing the model. So giving this bias label, supplying this bias label actually gives quite a bit of information. So depending on the availability of this extra information, we have a spectrum of difficulty in the settings. So in the easiest case, you have every information. You have some unbiased training samples as well, and you have every kind of Q labels available. So these are actually including Q labels which are beyond the bias label itself. It contains bias label, and on top of that you have some other interesting labels. In level 1 case, where you have slightly less information, but still essentially every information that's needed for debiasing the model, you have some unbiased samples as well as bias labels attached to every sample. Okay. And in level 2, you have some unbiased training samples, but you do not have the bias label. In other words, you do not have knowledge of which samples are actually unbiased samples. Okay. And finally, you have severest degree of difficulty, where all training samples are biased. So the claim here is that it's essentially impossible to solve, but I'm still going to talk about a few methods that are proposed under this setting. Okay, and make a comment on that. So let's first take a look at the easiest case, when you have some unbiased training samples as well as a variety of Q labels available per sample. So a suitable kind of data set for this kind of exhaustive labeling of attributes Qs, right, is a BERT dataset. It's called CUB dataset, that is beloved by computer vision researchers because of the well-defined problem of predicting the bird species, and because these are all birds, they all share common features like or share the similarities in the composition of attributes. Like they have heads, right? They have wings, they have legs, they have body, right? And because of the similarity of the body structure, you can actually predefine the set of attributes for each bird and assign the shape and color features for each part. So for example, here we have this kind of a bird species, and we can say, yeah, the forehead color for this bird is red, and there's certain breast pattern, there's wing color, which is like white and black in this case. So we annotate essentially every such bits of information for every bird species here. So these are annotated by experts in birds, okay? So let's say here the task is to tell which bird species this image contains. And as an intermediate step, we have all kinds of Q labels, Z, which contain forehead color, breast pattern, and so on, okay? So for this approach, you actually need quite extensive labeling annotations per sample. So you have to make sure the bird experts sit on the desk, and they need to kind of tell for each bird which attributes are present. And this is called concept bottoming model, when you have input layer at the beginning, and then eventually you wish to predict the label, the bird species. But in the intermediate layer, you have a bottleneck, which is the prediction of individual attributes. Okay, So instead of having a black box model, which is carrying the information from the input to the final output y, you have an intermediate bottleneck through which the prediction should be made. So you're forcing the model to make the final prediction of bird species based on the concepts or the attributes detected in the image. Okay, so there's no way other than predicting the right concepts to predict the right class for the image here. So the model is essentially a composition of two functions. So first of all, you have a CNN to predict each concept here. And based on each concept, you make a prediction, okay? Because we have the triplets of labelings, X, Z, and Y all the time, it's possible to train the first part, the concept extraction part, and the second bird species prediction task separately. So you can also train them separately. But in the paper, they propose to train everything jointly. Also including the training for the whole model from the input to the task label. Here we tend to have a very good control over the selection of cues for the model. So if you identify that the final prediction is relying on some cues which are not so reliable, then you can also explicitly remove the feature from making the prediction by making the corresponding predictions to be 0 all the time. So during the lecture, there was also a question of whether the initial part of the model, the CNN, which is predicting the concepts, may also rely on some biases, right? For example, for predicting the wing color, maybe the model is looking also at the background cues like like jungle or Arctic, or if it's ocean and so on. So it is totally possible that this may happen, right? But the idea here is that even for these kind of background cues, you can solve the problem by including them as one of the concepts. And if you include those as a new concept, you have again a control over which features are inducing, which features are actually present in the image. And you can also try to erase the dependence on these cues for making predictions eventually. But if there are dependencies among the concepts, then there should also be some special treatment of the concepts. So nowadays, the research trend is going towards the direction of understanding the dependencies among the concepts and building hierarchies, for example. So that's one interesting direction that's emerging these days. Another interesting direction that's emerging is the utilization of foundation models, especially vision language models. This is great because then you probably don't need to do the extensive annotation of the concepts for every image. That annotation procedure tend to cost quite a bit of annotation efforts because you have to make sure the experts sit down and do the annotations. So these kind of vision language models tend to replace the annotation procedure, and perform some zero-shot prediction of concepts, for example. So there's quite a bit of promise here with the foundation models, and there are exciting research opportunities here. With that, let's move on to the first scenario, the second scenario actually, level 1, where we have some unbiased training samples, as well as some bias labels available. So here the solution in a nutshell is you put more weights on unbiased samples, right? If there's a bias label, then you know right away what is unbiased sample, right? If the y and z are not equal. So since we have very small amount of unbiased samples, what we can do is to increase the weight for these samples during the training. In practice, that means you're going to put a factor multiplied to the loss value for every sample, and that's going to be based on the on whether y and z are equal to each other.
And now let's take a look at another method here, de-biasing representation. So let's say here again we have diagonal training samples, red circle and green triangle. Let's say these are 99% of the cases, but eventually we're interested in recognizing the shape. So we have the task labels 1, 1, 2, 2 corresponding to circle and triangles. If we train the network, including the embedding space in the middle for the task, then the model is very much likely to learn the color-biased representation. In other words, the embedding space itself becomes variant to different colors, because that's such an easy cue to learn. And exactly, so this is how it looks like when you normally train the network this way. So now what you can do is to kind of amplify the bias first by training a dedicated bias predictor on top of this embedding space. So in this case, you can use the bias labels now, Z labels, to predict the colors from the embedding space. And the losses to minimize the bias prediction, right? And this red line is going to be the learned decision boundary in that case. Now, the trick is to actually remove the information about color from the embedding space. In other words, you try to make the embedding space itself color invariant. And for that, what you can do is now you fix the decision boundary that's trained in the previous step. And then now, using the same set of labels, you now try to maximize the bias prediction loss with respect to the model that's embedding those points. Okay, so in other words, we are learning an embedding space anew, which is not helpful for achieving the bias prediction task. If you train it this way, then the decision boundary stays the same, and the samples become kind of indistinguishable from the perspective of color Q, like this. And now the embedding space is now conducive to recognizing the original Q that we are interested in, the shape, right? Because now it's invariant to color, but still variant to shape. Now what you can do is to train a network again on top of this embedding space and try to minimize the ground truth label prediction loss. And then eventually you're going to get a more favorable decision boundary that's now debiased. So this method is called domain adversarial neural network. So the network consists of 3 parts. So the green part is the stem part where the features are extracted into the embedding space. You have 2 classifiers on top. So one is for the task classification and the other one is for bias classification, which is written down here as a domain label. And the task for the classifiers is to do the classification well. But when you train the features, the class loss gradient goes without any modification, but the gradient from the domain classifier gets reversed. In other words, you're doing the opposite optimization problem for that objective. If you write this down in algorithm, you have something like this. So you can write down the loss function as a loss based on the composition of the stem parts GF and the classification part GY, and you have the loss for the domain based on GF again, and GD, which is doing the classification for the bias label. And the training objective for F is again loss minimization for LY, or loss maximization for LD. And for training theta Y and theta D, which are classifiers, you have gradient descent basically. So that was the method for doing debiasing when there's some unbiased training samples and attached bias labels. So you basically know which ones are biased samples. And now let's jump into the case when you have some unbiased training samples as before, but there's no bias label or whatsoever. What can we do in that case? So the solution in a nutshell here is you can detect unbiased samples and then put more weights on these samples to debias the model again. This setting is quite realistic. You're going to see a lot of these cases in real life. First of all, you're going to see a lot of training samples where the unbiased samples are very rare, and most of the samples are actually coming from some biased distribution. And of course, you're only going to see the task labels, and there's not going to be any bias label. So this scenario is very interesting from practical perspective. So let's see how we can solve the problem here. To solve the problem here, we need further assumptions on bias, actually. So typical example of such a bias, such an assumption is the bias is the first cue that is learned by a generic model. Because the bias is something that is super simple to learn, so the model likes to learn that first and then perhaps learn the other cues later on in the training stages. Or bias can be the cue that is learned by the model of certain limited capacity. Okay, it's again a simple cue that is now the bias, and so model with even simple limited capacity can learn that signal. Right, so with that kind of assumption, what you can do is to train an intentionally biased model. It is difficult to train a de-biased model in the first place. What you can do instead is to train a model that is even more biased than a model would normally be. So example of such intentionally biased model is again models that are favoring simpler cues, like the model trained for a very small number of epochs or iterations, or it could be a CNN with very small receptive field, or a transformer with shallower depth, or you might have a kind of multimodality task like image and vision, but you can introduce a model which is only looking at a single modality at a time. So you have limited input to the model. So these are in general simpler models than usual, and these are aimed to detect or utilize the simple cues much more strongly than usual. And now, having trained the intentionally biased model, what you can do is you finally introduce the final model that we wish to train eventually, and say this model has to be perceiving the world in a different way from the intentionally biased model. So you learn to be different. So there's going to be task supervision for the model, of course. There's also going to be a regularization, which is making this final model different from the intentionally biased model. Okay, so what I'm going to do is to introduce a few examples of these intentionally biased model and final model sequentially. So the first method in this section, in this scenario, is learning from failure. Here you have two models, the green model and red model here. The green model is the final model that you wish to train, and red one is the one that is intentionally biased. So I'm going to explain how one could train an intentionally biased model, and then introduce the term that is making these two models different. So let's take a look at the red model first. Normally for a classification task, you would use cross entropy. But here you use generalized cross entropy, which is 1 minus py to the power of q divided by q. Okay, so if you're familiar with calculus, you can see that as q approaches 0, the generalized cross entropy approaches to cross entropy again. Okay, so now what happens if q is greater than 0? So we now know that generalized cross entropy is indeed a generalization of cross entropy. To look at the effect of q, we can take a look at the gradient. So which supervision signal does the model get when q is greater than 0? If you look at the gradient, it turns out that the gradient with respect to the parameters is actually a scalar multiple of the original gradient for the parameters, where the factor is p to the power of q, where py is the confidence level for the ground truth. So my claim here is that this loss function strengthens the initial predictions over time. To understand why this is the case, we can think about the very first few iterations of model training. In the very first iteration, when there was no update whatsoever, the model would make a lot of wrong predictions in the first place, and therefore py will be very low. So it will actually be very low for most of the samples. But after one iteration, the model will quickly learn to predict well for very simple examples, easy examples. So for these easy examples, actually, the py values will be very close to 1 because you're doing well already for these samples. Okay. So when py is close to 1, then the factor here, py to the power of q, will be also close to 1, and so you're going to get the full gradient signals from cross entropy as before. But let's say there's a very hard example where the model fails to learn it in the first iteration. Then the py value for that sample will be still quite low, if not the first few iterations. And therefore, py to the power of q will be also rather low. Okay, the greater the q is, this factor will be even lower for harder samples. So what this means is if the model fails to do well for certain samples, then the model will basically just, this loss function is encouraging the model to give up on these samples. In other words, easy samples will be trained over and over again over iterations, while the harder samples will not be trained. So here we are amplifying the simple cases in the first few iterations, and the crucial assumption we have on bias here is that the biases are the cues that are learned first. Okay. Of course, this assumption is not always the case. And of course, the signal is the one that you wish to learn in the first iteration. The signal is the one that the model learns in the first few iterations. In that case, you should not do this. But if you have the knowledge that bias is something that is learned first by the model in general, then you can use this kind of bias amplification scheme. Afterwards, what you do is introduce this final model that you wish to train. And based on the prediction performance on individual samples, you determine the relative weights for each sample for training this green model. The weight for each sample X is defined by this division between cross entropy of the prediction by the bias model and the summation of the prediction from the bias model and the original model. So let's split the case here and see what happens if the cross entropy from the bias model is 0. Okay. In other words, that sample is super easy for bias model. then the weight here becomes 0, which means that you're not actually training the green model with this sample. On the other hand, when the cross-entropy value for the sample is high for the bias model, then you're going to have a very big value for this one and this one here, and a relatively smaller or similar value for FD. And so the WX will be larger in general. It's still going to be less than 1 for any combination here, but still it's going to be rather large. And so the green model will be trained even more on that sample. So in other words, how you train the green model is basically by taking a look at the prediction performance by the red model, and if it's a hard sample, then you give more weight. So that's rather simple. Again, we train an intentionally biased model, and you train a final model by using some regularization in the form of B difference supervision. Let's take a look at another example of how to encode the B difference supervision. So again, we have a final model, let's say, which is F, and we have intentionally biased model, which is G. But let's be more precise here and write down F tilde for the softmax value. And F is basically the logit value, the pre-softmax values. Okay, and softmax here is again mapping a real valued vector into a probability vector. Product of expert is defined by a loss function minus log of p, which is identical to usual cross-entropy loss or negative log likelihood loss. And here the p function is a combination of individual models in the ensemble, or each expert. So py, the final prediction for class y for f and g is essentially the L1 normalized L1 normalized individual products of probabilities. So you have individual probabilities F tilde and G tilde, and you just do pointwise multiplication for every class. And then, of course, you have to do some normalization to make this into a probability vector. And that's called product of experts. How do you compute product of experts in practice? Normally you do, so eventually you're putting a minus log loss value on top of the softmax. So you can think of this as a softmax. If you put log in front of everything, then x then log, right? Then this is exactly the format of softmax, right? So you can write down the loss as minus log of softmax of, again, the log values of the f tilde and g tilde. And now it's a plus here because of the logarithm of the multiplication. And if you think about the logarithm of f tilde, it's actually identical to f of x plus some constant c. Likewise for gx, right? And we can safely drop the constant c here because we again have a softmax. Remember that softmax function is invariant to translations. And so you can omit any constant value added to the operand. Okay, so in practice, product of expert is fairly easy. You just sum over all the individual logit values from the network, from different experts, and then you put a softmax on top, and then apply the negative log likelihood on top. So the method is very easy, but now the question is how does that encourage different solutions for f and g? So for that, we have to recall how the gradient for cross entropy looks like. So if you take the gradient with respect to the logit values, especially the index I, right, for the cross entropy loss, what you get is delta IY minus softmax of I, F. So in other words, it's a one-hot vector minus the probability vector. So far, so good. Now, if you take the gradient of the product of expert loss for, again, for f, right? Then what you get is 1 vector minus softmax. But now the softmax is over the summation of f and g. Okay, so it's still very easy. But now, this summation of f and g already makes f and g to be different. To see why that is the case, we can take a look at the gradients again. So how does the cross-entropy gradient work? Let's say the ground truth is y equals 0, and let's say f is rather correct. So your prediction is already centered around y equals 0. In that case, the additional, the difference between one-off vector and the prediction vector is indicated by this red region and blue region. And the size of the gradient is overall quite small. But let's say f is rather wrong, meaning that the prediction probability for y equals to 0 case is smaller. In that case, you're going to have a much larger gap between the one-off vector and the prediction. And so gradient will be larger overall. So now let's take a look at the case for the product of experts. Let's say f is somewhat wrong, but g is like outright wrong for the prediction task, right? And the softmax of the summation, which is the product of expert prediction, is some average between these two, right? Somewhere in the middle. So normally, f would have not got so much penalty, right? Because f is rather not super wrong, right? So there was going to be a rather smaller smaller gradient. But now for the product of expert, because of g, which is outright wrong, the product of expert is also more wrong than f alone. And so the gradient for the product expert is larger than f alone. But now the gradient that is training f is actually generated against the product of experts. So even if f would normally get very small gradients, f would now get even more penalty for the wrongdoing of g. Okay. So as long as g is doing something wrong, f is getting more supervision. Okay. So now we can think about the case again where g is kind of intentionally biased model, and g is making mistakes on some samples. What happens is for those samples where g is making mistakes, f is going to get even more more supervision than before. So that sounds familiar as before, right? Because now for the samples where g is doing not right, f is going to get more signals, more supervision. So in that way, f is trained to be different from g. So one example where this product of expert was applied was in visual question answering. In visual question answering task, you ask the question about an image, given image. For example, given this image, what is the color of the grass? And the answer here is yellow, of course, or brown, right, like here. But normally, those kind of BQA models tend to have strong bias towards language-only cues. So when the model is asked what is the color of the grass, it would probably not take a look at the image pixels that much and just say, yeah, it's grass, and so it should be green. So what you do here is you amplify this bias again with a model which is looking only at the question, not the visual part. And then the model is going to produce green here. And you do product of expert here. And then this product expert makes sure that the final model gets more penalty for making this wrong choice on this sample. Okay, so here we looked at the intentionally biased model, which is based only on certain part of the input, like single modality, when the task is multimodality. And the final model is trained by putting a B-difference supervision here again, using product of experts. Now let's take a look at the third and final example. So I'm going to talk about texture bias and some similar kinds of biases in networks. So it is known that if you train a image classifier on ImageNet kind of data sets, you actually introduce quite a bit of texture bias. That means the model is not actually looking at shapes, but only looking at texture. So for example, given its original image, you can do multiple transformations on the image, like grayscale, silhouette, right? But in the case of silhouette, all the textures are gone. Just the shape is there. And in that case, you're going to see quite a bit of drop in performance for most of the models. The left 4 bars are basically the performances by models, and the rightmost red bar is the performance by humans. So it kind of shows that humans are more resilient to shape than the models are. But on the other hand, if you just retain the texture and remove the shape, like this figure here, then humans are not very good in this case, like 90%. So that's about 10% point drop, whereas the models are not super that much affected by this change. Okay, so that means models are favoring texture cues much more than humans do over shape. So here again, the question is how to intentionally bias a model to only look at texture. Here the claim is that a model can be made to look only at texture by reducing the receptive field. Well, we are talking about convolution neural networks here. So normally, if it's ResNet, you're going to have a bunch of 3x3 convolutions over layers. And what receptive field here means is the combination of the increase of the domain of influence as you go down the layers. So given a single pixel at the topmost feature layer, you try to infer back what is the region of influence for making any change in that single pixel in the feature map. And you can infer out what is the eventual kind of field of view or receptive field for that pixel. And normally it's huge. Even for a single pixel in the feature map, you're normally going to see that the corresponding receptive fields goes beyond the image boundary itself. So every part of the image is affecting every single feature pixel above. So in other words, those CNN models are actually, by definition, capable of handling both local and global cues. But the problem is that if you train with ImageNet-like data sets, they don't actually need to look at the global cues or the shape. And it's actually sufficient to just look at local cues to make the prediction. So here what we can do to intentionally bias model is by reducing the kernel sizes across multiple layers. And then you're going to end up with one-by-one convolutions all the way through the network. And that's going to make the model do the reasoning over a small region at a time. So this kind of model can only capture local cues like texture. So this is another example of intentionally biasing model. So our model is eventually to large receptive field, but we have introduced an intentionally biased model using smaller receptive fields. Now the question is how to encode the B-difference supervision. We do that through statistical independence on the representation space. And this is measured with HSIC, or Hilbert-Schmidt independence criterion. I'm going to explain a bit on what Hilbert-Schmidt independence criterion here is. So its mathematical definition, original definition is based on the Hilbert space, and based on some generalization of covariance matrix to nonlinear high-order moments. And then you take this infinite dimensional norm, Hilbert-Schmidt norm, on the Hilbert space, infinite dimensional space. And after some involved derivation, you end up with the statement saying if you take the Hilbert-Schmidt criterion between two random variables, and if it's 0, then it means u and v, the two random variables, are independent, and vice versa. So it's a very strong test for independence. And another nice thing is that it's fully differentiable. So it can be used for regularizing a neural network using stochastic gradient descent. So now the question is, how do you compute HSig in practice, and what does that actually mean? So instead of the infinite dimensional case, I'm going to look at the estimator based on finite samples. So let's say we take m samples from each of the random variable u and v, okay? And then we're going to build kernel matrices Kij and Lij based on some characteristic kernel like RBF kernel with some hyperparameter sigma. So that these are going to be similarity matrices. And you take the row-wise mean out, so that centers every row in the matrix, in the similarity matrix, around 0. And then what you do is you do matrix multiplication between these two and take the trace of that. What does that actually mean, right? So let's take a look at an example here. So let's say the samples from U are looking like this and from V are like this. One note here is that U and V may actually be in totally different spaces. There's no requirement for them to be in the same space or whatsoever. But we have to always sample these jointly. Otherwise, we do not see their independence or dependence. So we sample jointly, and we measure the pairwise similarities using kernels. And on the diagonals, we're going to see ones throughout because the distance is 0 for the same vectors. And off diagonal, you're going to see some different patterns between the blue part and the red part. And what you do afterwards is to take the row-wise mean out, and you're going to have some positive values and negative values. Positive means your similarity is higher than the row-wise average. Negative means the other way around. And then you take the matrix multiplication and take the trace. Now we have a small note here saying if you take the matrix multiplication and do the trace, what you actually do is to sum over all the indices after doing element-wise multiplication. So in other words, what this is actually doing is computing the dot product between two flattened matrices, right? And by the way, the HSig value can always be non-negative. So what this really means in practice is you're aiming for orthogonality between the similarity, the row-wise subtracted, mean subtracted similarity matrices. So you're aiming for orthogonality between these two vectors or factorized matrices. So in other words, you're trying to make sure that the number of positives and negatives are rather similar. Now, the trace for this particular case is 0.537. This is kind of measuring the degree of independence. Now, let's take a look at the case where the dependence, where it's more extreme. So let's say it's completely identical kind of similarities across these two. In that case, you have much less independence, right? Or more dependence. And the HSig value in that case is 1.353. So by this, we can see kind of that minimizing this HSig encourages differences in similarity patterns for U and V matrices. Okay. And now let's take a look at the case when the the points are actually not samples from some random variable per se, but actually function outputs from some input distribution, but with different functions, f and g. These are still valid random variables, right? Because you're taking the output of the two functions based on the same distribution x. Okay, so u is now f of x and g is now g of x. So the question is, what does it mean to minimize the h-sig on f of x and g of x? Okay, so here the claim is that it actually encourages the similarity patterns for f and g to be different. So for example, here on the left case, we have more similarity for this red triangle and red square. But on the right case, we have more similarity between red square and green square. In other words, the left space learns this invariance with respect to color. On the right space, you see invariance with respect to shape. So they learn different invariances.
Now I'd like to make a small theoretical comment on theoretical properties of h-sig functions. So this is trying to characterize what it actually means to make two functions to be independent to each other, given probabilistic random variable as an input. So let's say we have two functions which are linear. So f of x is ax plus b, and gx is bx plus b. And let's make a further simplifying assumption saying the x is now a normally distributed random variable according to mu and sigma. Then we argue that h-sig of h of x and g of x is equal to 0 if and only if we already know that this is happening if and only if f and g, or f of x and g of x, are independent, statistically independent. And now we are saying that is happening if and only if the kernel of the matrix A and kernel of matrix B, their orthogonal spaces are orthogonal to each other. Okay, so here kernel of A means the kernel space of the matrix, and the orthogonality superscript means you're taking the orthogonal space of the kernel space. And for two vector spaces S and T, them being orthogonal with respect to some positive definite matrix, actually semi-definite matrix sigma, means that for every member of the vector spaces S and T, their inner product where there's this semi-definite matrix in between, the inner product is always 0. So it's kind of a version of orthogonality between the two spaces. So what does that actually mean, right? So you can interpret kernel of A as the space of invariances for f, because the changes there do not change the function output of f. And now kernel A of the orthogonal space of that is the space of factors that vary f's outputs. In other words, these are variances of f. So what this statement means is the variance for f and g, these are orthogonal to each other. So these are completely different axes that changes that vary the output of f and g functions. So in other words, the minimization of h-sig is the encouragement of the different functions to learn different factors, which is what we want. So this is just a piece of kind of intuition, and this is not part of examinable material. Okay, so now the question is how to use this h-sig criterion for actually optimizing the models to be different. For that, we introduced this function space viewpoint for architectures. So I'd like to argue that when we define an architecture, neural network architecture, we are actually defining a function space. For example, if we come up with a function space defined by architecture ResNet 50, then that's essentially a collection of all kinds of functions that can be parameterized with this architecture. And now we have a second subspace, which is architecturally constrained. And now what's important is that this intentionally biased model or architecturally constrained model is actually encoding a subset of the original space. So in this case, we are shrinking the kernel sizes of the convolutional filters. And it turns out that you can actually simulate those small kernel sizes with a larger kernels by padding zeros or inserting zeros in the outermost indices, outermost cells of the kernel matrices. By doing so, you're encoding. So by thinking this way, we see that the architecturally constrained space G is a proper subset of F. And that is a critical property for doing our optimization here. So if you just train the F model, which is the original model to be optimized, they turn out to be utilizing only a small fraction of the actual function. And so conceptually, we can think of this as F being part of G. In other words, it has a lot of bias factors inside. And now what you do with the second network is you try to make it mimic F as much as possible. And the role of F is to run away from G as much as possible. So the objective for G is to do well on the original task loss, but at the same time get closer to F. So you're minimizing independence between F and G. So you maximize the h-sig value like this. So you go like one step like this, and then the task for F is to run away from G. So you have to minimize h-sig value to maximize independence while solving the original task, obviously. And you run away like this, and this continues on and on until F is actually outside the domain of G. And G cannot chase after F anymore because G is constrained. And F is now outside of the G area, and that actually means by definition F is de-biased because F is now utilizing features that cannot be represented by the intentionally biased model. So that is great. In short, we are solving this minimax game of F and G. So for F, the goal is to solve the task well. For G, also the goal is to solve the task well. It's just that the goal of F is to run away from G, and the goal of G is to chase after F. Okay. So how does it work in practice? Let's say we have a very toyish setting where you have MNIST digits like from 0 to 9. But let's say the background color is correlated with the signal, with the digits. If you train a model on this kind of data set, almost certainly the model will pick up color as the most critical factor, because that's such an easy cue to look at. Right, so for evaluation, we have two different cases. So one biased test set, and the other one is unbiased test set. Where unbiased test set will have decorrelated background color and the digits that's printed out in the image. So if you just rely on color, then you're not going to do super well on unbiased data set. You're actually going to achieve random chance, 10% accuracy there. And now we have biased MNIST model. So how are we going to capture this intentional bias to color? So one possibility is just to replace all the 7x7 or 3x3 convolutions by 1x1 convolutions. If you have 1x1 convolutions throughout the layers, then the final features will only look at a single pixel at a time. And so that makes the model be only aware of pixel level reasoning. And so that intentionally biases the model to only looking at colors. So for the original model, if you just train it in a vanilla way, because color is such a strong cue, the model will achieve close to random chance, 33% accuracy. And the intentionally biased model is built to be just biased to color, so it achieves 10% random chance. But when you do the B-difference supervision between F and G, what you get is 64%, which is much better than the baseline 33%. So it seems to work here. Now with action recognition, there is a very well-known bias in those recognition tasks. For example, when you try to train the models to see actions, the models actually learn to look at the background pixels or the objects in the scene. It's called static bias. You do not actually see the movement of bodies or actions to make the prediction. You just look at static stuff to make the prediction. For canoeing or kayaking, you don't actually have to see people paddling. You just need to see that there's a kayak boat and there's some river. For applying cream, you just need to see that, there's skin texture and there's some hand kind of shape. And that's enough to tell, this is actually applying cream action. So for testing whether the model has overfit to this kind of static bias, people have introduced a new evaluation data set where they decorrelated the actions from the background. So they do kayaking action in the in some indoor scene or surfing in the indoor scene. Okay. And for debiasing this kind of factors, we introduced an intentionally biased model here again. The original model is based on 3D convolutions. So for every layer, there's a consideration of the volumetric reasoning of 2 + 1 dimensions. So there's 2D dimensions for the space, but there's 1 dimension for time. And you're kind of looking at tiny windows of action LEDs, which are then combined architecturally, hierarchically into final decision of what the actual action is. But even if you have this kind of complicated model for inferring the individual movements and actions throughout the scene, the model does not actually utilize the capacity here, but they just decide to just look at static factors because the data set is so easy that you're just allowed to use that to solve the task. So we introduced the intentionally biased model here, which is only capturing static cues. So for that, we introduced 2D resnets and do the unsampling of across multiple frames. So these individual predictions are basically based on each static frame, and so it does not have any reasoning over any time axis. And then you simply aggregate the predictions across different frames. So if you take a look at the original model, it gives you 18.9% unbiased accuracy, meaning that it's highly biased. Intentionally biased model gives you around the same kind of accuracy, 18.4%. But if you do this kind of debiasing using the intentionally biased model, then you get slightly better performance here, 22.4%. So it seems to work here a little bit as well. In general, I like to call this myopic models. Even if the model has the full capacity to see the global structure of the data, the simplicity of the data set allows the model to just focus on simpler cues. And if there are 2 cues given to the model, simple cue and complex cue, then almost always the model chooses to use simpler cue. And so it's not utilizing the full capacity of the model. When that happens, what you can do is to introduce a second model, which is intentionally confined to simpler queues, and then let the original model, encourage the original model to be different from this intentionally confined model. So another example is language model. They are also known to focus on word level queues in many cases. Let's say the task is sentiment classification, and you can basically tell in certain data sets whether the sentiment is positive or negative by just counting the number of nots in the sentence. But you know, if there are even number of nots, it's actually a positive statement, right? So, and these cases are probably not very well represented in the data set. So what you can do here again is you have some original model, which is complex enough, like BERT model. And you have an intentionally biased model, which can only look at single word at a time and then doing some aggregation on top. So one could use word embeddings, for example, here. And then you put some B-difference supervision here to make sure that the BERT model is actually utilizing queues that models of such complexity can only do. So far, we have looked into 3 different methods: learning from failure, product of experts, and rebias. In each case, we looked into intentionally biased model and how to encourage the original model to be different from this intentionally biased model. For intentionally biased model, we looked into different options. So first one was a model that is favoring earlier predictions. Here, the assumption is that the bias is more quickly learned. In the second case, we looked into models taking only single modality inputs when the task is actually multimodal, like vision and language. So here, the bias that has been observed is some features that is only looking at a single modality. So even if you give 2 different modalities, the model eventually learns to use only one of them. And we wish to prevent that. And so we train an intentionally biased model only based on a single modality input. Finally, we have architecturally constrained models to make sure that if you have a complex original model, you want to make sure that this model is making use of its full capacity. Okay, so here the bias is the feature that is learnable by only a constrained model. And for encouraging different representations, we looked into 3 different options. So the first one was to put different loss weights on samples where the bias model makes mistakes. So for these samples, this original model will put more weight, and therefore these are generally corresponding to unbiased samples, and the model will also be less biased. For product of experts, we looked into the gradient, and it turns out that product of expert is amplifying the gradients for samples where the bias model makes mistakes again. So that's another version of putting more weight on the samples with that the bias model find it hard to predict. In the final case, we looked into H-seq regularization, where the goal was to encourage learning different invariances or different variances. So there's no strict rule that states that you have to always use pairs here. You can also mix and match different ingredients here for intentionally biased model and encouragement of different representations. So in principle, you can also come up with 9 different combinations here. Of course, if you have other ways to encourage different representations, you are going to have much more possibilities here. Okay, so that was it for the important section of unbiased training samples with no bias label. And now let's take a look at the case when you have only biased samples. Is there something we can do about that? So this is the case, right? You have 100% biased samples. Is there anything we can do about that? So what people have proposed was one could perhaps train multiple models with diverse out-of-distribution behaviors. What does that mean? So you can train a model like this, right? And the off-diagonal region here, upper triangular and lower triangular regions are the regions where the behavior is not very well defined. So the model is free to do whatever it wishes to do. So let's say the first model just chooses to do like this horizontal decision boundary outside the training domain. Okay, so that roughly corresponds to this kind of rule for off-diagonal samples. And let's say we train a second model and it kind of learns a different rule outside the training domain. And let's say a third model is also learning something different. Okay, so if it's possible to come up with those kind of three different models who have different behaviors outside the training domain, what we can actually do at test time is we label a few samples from the test distribution, right? So we have a few samples like from this unbiased data set. And based on the performance of those three models on this data set, we may be able to choose the model that's doing the right job. In this case, model 1 is actually doing the right job, so perhaps it's possible to just select model 1 at test time. Okay. So in this case, you're actually also making use of some deployment data, right, to do the model selection. But we're kind of keeping it minimal to make sure that it's still realistic. Yeah, of course, it's not a fair comparison against the other ones, right, where we do not have access to any test time resources, but we assume that some unbiased samples were available during training. So it's kind of similar, but here we are really trying to minimize the amount of information from the deployment scenario. Okay, so what are typical recipes here? So you have the original, so first of all, you have M different models here that we wish to diversify. So they're all going to have more or less similar behavior on the training set, the diagonal training set, but we wish to make sure that they have different behaviors outside the training domain. How is that possible? You first of all train all the models using the original task loss cross entropy. Here, by the way, the Z refers to the training samples, x1, y1 up to xn, yn. And on top of that, you put some regularization factor for every pair of models, f1 up to fm. You want them to be kind of doing different things. Okay, so I would like to call this diversity regularization. For that, actually, you could actually use all the previous ingredients for making the two models behave differently. That is, you can also put like different weights for different models on different solutions, or you can also use regularization like HSIG, or you can also do product of experts if you like. But here I'm going to talk about two more diversification strategies. So one strategy is more input space perspective. So you can define the diversity loss as the cosine similarity between the gradients of the logit value with respect to the ground truth class. Okay, so Fy refers to the logit value of the ground truth class, and M and L here refers to the index for the expert, the model. And you try to make sure that these gradients are orthogonal to each other. Why does that help? It helps. Intuitively, because for every point, you are trying to make sure that the direction of increasing score for y are orthogonal. And if you do that for every input point, like on this diagram, it kind of encourages the decision boundaries to be orthogonal to each other. If they're orthogonal to each other, then their behaviors outside the training domain are maximally different. So that is the rough intuition of this method. In the paper, they also make a claim that it has connections to statistical independence of the output of the function, where the x is now a small perturbation around the original training point. Yeah, so you're introducing this isotropic noise around the training point with some small factor epsilon, and the independence between these two random variables through f is roughly equal to the independence between the gradients, or the orthogonality of the gradients. Yeah, so that's, by the way, non-examinable. And now we have more output space diversification as well. Here, the intuition is that we wish to make sure the models output different predictions for the same set of inputs. So again, x here is a random variable, and the prediction f. Okay, so prediction fm tilde means the probability vector. So in the first term, we are looking into the joint distribution of fm and fl. So for the same input, we make a matrix showing what is the pattern of predictions. If fm and fl are always equal, then you're going to see highly diagonally concentrated matrix of predictions for fm and fl. If they are fairly independent, then you're going to see more well-spread distribution. And now on the left, we compare that joint distribution against the product of the marginals. So this is typical test for independence for finite or categorical random variables. So we just apply, so it's a version of HSIG, but on a categorical random variable. So in the HSIG case, we are doing that on the continuous space of embedding space, but now we are doing the same thing on the discrete space of predictions. Although KL divergence and HSIG are slightly different, but still they're zero if and only if they achieve, the predictions are independent. So in that sense, there are some connections. In practice, how you compute this KL divergence? First, the starting point is this tensor called PBMC. You have three axes for the tensor, so three-dimensional tensor. The first axis is B, the batch size, which is encoding the samples in X, samples of X. And the second index is M, which is encoding the number of experts. The final one is indexing the class. Okay, so for every sample, for every model, you're gonna it's gonna give you a vector of possible predictions. It's gonna sum to 1 for every B and M. If you sum over C, and now using this tensor, you're gonna come up with the marginal tensor and the joint tensor. And how you get the marginal is basically you take the product between these two estimated probabilities. So by summing over, by averaging over B, you're inferring the prediction for each model M across all the classes. And you do the same thing for the second model L, and for this free index D, which is encoding the class again. So eventually you're going to have, for every pair of models, for every pair of class index, you're going to get some probability value. For the joint, you're looking at the sample index, which are now joint. So you take the multiplication of PBMC and PBLD and then sum over B, instead of summing them over first and then doing the multiplication. Okay, so now you take the KL divergence by taking the logarithm of the division of joint and marginal, and then you do the average according to the distribution of joint. Okay, and that's going to give you a KL divergence. And if you minimize this loss function, then you're encouraging the independence of the predictions on the same set of inputs. Yeah, so that's another nice way of doing encouraging diversification. Now I'd like to mention a few notes on our unofficial preliminary findings. So we are doing some preliminary studies around the actual efficacy of model diversification methods with Alex from our group. And so here the core assumption for diversification of model is that even with just diagonal samples, you can actually achieve meaningful diversity of models on the off-diagonal samples. But we are highly doubting if that is the case. In many of the previous methods doing diversification, it turns out that the models, the data sets where these models are trained on seem to contain quite a bit of unbiased samples, the off-diagonal samples. And therefore, it is making the task of diversification a bit easier. And if we make it really harsh, that we have 100% diagonal samples, it turns out that it's kind of hard to diversify the model on the truly off-diagonal samples. So it kind of gives us a hunch whether the model is strongly guided by some inductive bias or something to really pick up more or less the same cue for doing the recognition on the off-diagonal samples. So if that is the case, then the scenario 3 does not make sense anymore. It is not possible to diversify the model based on only biased samples, and then model selection is not possible. So this again comes back to the question of whether it's fundamentally impossible to select the right cues with only biased data. Okay, so with that, we have covered the interesting scenarios in the space. If you have any questions or feedback, please submit them through the link here. Thank you.